Hello everyone and welcome to another episode of the show. I'm your host Tyler Kern. Thank you so much for joining us here today. On this episode, we're going to be talking about liquid cooling, why some people have begun to use it, some of the different types, and so much more. And joining me here to talk about all things liquid cooling today is Austin Hypes. He's the Chief Technologist and VP of Engineering at UNICOM Engineering. Austin, welcome.
Well, thank you. Thank you for having me.
Absolutely thrilled to have you along here today, Austin. So let's start off here. Before we dive into the questions and start talking about liquid cooling, you are the VP of Engineering at a company with engineering in the name. So it sounds like you do a lot of important things. Tell us a little bit about your role at UNICOM.
Yeah, so at UNICOM, I pretty much handle all the front-facing engineering and design engineering for the company. Multiple teams under me, from sales engineering, consulting with customers, finding out their needs, through the design and validation process before we hand off to manufacturing.
Excellent stuff. So let's dive into our primary topic here today. Why are people turning to liquid cooling on a more regular basis these days?
Yeah, so there's multiple reasons. Liquid cooling, first and foremost, it's a lot more energy efficient than traditional air cooling. Part of that comes with data centers trying to consume less power, or more importantly, make sure the power they're consuming is going to useful work, as opposed to things like air conditioning. So it also allows for greater densities. So areas that have less space for a data center, you can put more high-performance computing in a smaller area when you have more efficient cooling. And then lastly, it allows platforms, especially servers and accelerators, to go in areas that aren't traditional data centers. You know, when you need something, on a street corner or more regionally focused, it allows you to put high-performance compute in non-traditional compute environments.
Interesting. So I know that there are different types of liquid cooling, right? So let's talk a little bit more about those different types and break those down for us.
Sure. First, you have what we call DCLC, or direct-to-chip liquid cooling, sometimes also referred to as cold plate cooling or liquid-to-chip. And that's more of a traditional, I think of it kind of like the radiator in your car cooling your engine, where you have special plates that just take liquid similar to radiator fluid, circulate it around, pull heat off of hot chips. But then there's newer types and more efficient types, mainly in immersion cooling. In immersion, there's even a couple of different flavors. You have single phase, and then you have two-phase immersion.
So let's dive into those different types of immersion, then the single and two-phase. Let's talk a little bit more about those in depth. Tell us more about those.
Yeah, so in single phase, it's just what it sounds like. You have a fluid that stays in one phase. It stays a liquid. And it's a lot easier for folks to understand. You essentially have a big tank with special engineered fluids. Servers and other compute equipment goes into those tanks. And instead of being cooled by fans pushing air through, there's pumps that just circulate the fluid through, and it's a much more efficient conductor of the heat. So it takes a lot less energy to push that fluid around and cool those hot chips than it does, if you were to, like I said, use air and a lot of fans and things to do that. That's different from two-phase, and two-phase, as the name implies, you're actually changing the state of that engineered fluid. So it goes from a liquid to a boiling action. And that boiling is actually the heat removal process. So it can be extremely efficient, obviously a little more complex because you don't want that very expensive engineered fluid escaping as vapor. So you condense it back down and recirculate it back into the tank.
So let's circle back and talk a little bit more about direct-to-chip liquid cooling. Give us some of the advantages and disadvantages of this method.
Sure. So direct-to-chip, one of the primary advantages is it can go into more traditional, data centers. It can go into standard racks. It has to be retrofitted, of course, and it's less invasive to the service. You're basically replacing what used to be heat sinks with these cold plates that have, basically a cold fluid in, a warm fluid out. Circulating through, like I said, very much like a radiator in a car, to get heat away from those hottest chips. So data centers that have been around for a while, it's a lot easier to put in. You're not putting in big new tanks. You're able to retrofit or put new racks into place to do that, so long as you have the plumbing and things to support them.
So let's do the same thing with immersion cooling. Give us some of the advantages and disadvantages, and maybe some of the different settings where you would use this.
Sure. So with both types of immersion cooling, with both the single phase and two phase, first primary advantage is you get 100% heat capture, and the entire server is going into the tank, meaning all of the chips, all the silicon is being cooled by that fluid, so you can capture it all and very efficiently recirculate it. That, in most environments, completely eliminates the need for any type of air conditioning. So that's why a lot of folks and a lot of data centers do look at it, because, like I said, it can go into those very hot environments. You don't have to keep the air cool. Additionally, our chips, our CPUs, they keep getting hotter. Accelerators keep getting hotter. They need more power. Right now, top of the line, chips from Intel and AMD, they're 270, 280 watts, very quickly moving to 350. And as we look at the next couple of years, 500 to 700 watts per chip is extremely possible and will be coming. With that, you simply cannot cool those with traditional air-cooled heat sinks in the form factors that exist today. You have to go bigger and bigger. So it was a 1U server, might have to be a 2U server, even bigger, because you got to have that bigger hunk of metal on there to blow more air through to cool that 350, that 400, that 500 watt CPU. Well, with liquid cooling, all three types actually, but especially immersion cooling, you can keep those servers into those much smaller footprints. So you can still cool those very hot chips in a 1U type of server design, so you can fit more of them in a smaller space. And like I said, a lot more efficient by not having all those fans trying to blow all that air to keep chips cool.
Is there a sense in which this, in discussing liquid cooling, it's worth thinking about and planning for the future and planning for, like you mentioned, the continued development of these chips and that sort of thing?
Yeah, so folks who want density, they absolutely have to start looking at their data centers and their environments. There's a lot of ways to go there. Like I said, if you're traditional racks, you still need usually some type of water cooling loop, some type of heat exchanger to go through there. Same thing in data centers that are looking at moving to immersion. If you already have that water loop in place that's already going to chillers, you're a good chunk of the way there. It's just making sure that your floors can support the extra weight, which is nice for a lot of places. You can go right down on a concrete slab as opposed to having to have a raised floor and things like that. But also, as we continue to look forward in the future, one of the advantages with some of the newer types of immersion cooling is you can start using what we refer to as dry coolers. And these are where you don't have a big chiller with an evaporative, cooling type of mechanism. You are actually utilizing what amounts to a radiator with a big fan. So you got the colder water after it kind of exchanges the heat with the equipment, getting warmed up. It's headed back. Now that water, as it warms up in a hot environment, might be leaving at 55, 60, 65 degrees Celsius. So even in very warm environments where it might be 40 or 45 degrees outside, over 100 Fahrenheit, you can get enough air blowing through there. You can cool that water back down enough to complete the loop, and much more efficient than a lot of the chillers of today, which rely on evaporative process. Right. Obviously, everyone's trying to be more environmentally conscious, so not evaporating a lot of water to keep your equipment cool, even though it saves energy, is a big plus for a lot of new data centers as well.
Absolutely, and we'll talk a little bit more about sustainability here in just a moment, but circling back to the single-phase versus two-phase conversation, when might somebody use one versus the other? Are there certain settings or opportunities where single-phase is maybe preferred or two-phase is preferred? Sure.
Single-phase definitely has a lower cost of entry. The fluids utilized in single-phase tend to be hydrocarbon derivatives. So think really, really fancy motor oil. Not quite motor oil, but kind of along the same process. As a result, per gallon, much less expensive. Also, you're not trying, because it doesn't evaporate, you're not trying to recapture it and condense it back down like you would in a two-phase environment. So the initial cost of entry is definitely lower in a single-phase environment versus two-phase. Now, two-phase, on the other hand, because it uses this phase change mechanism to eject the heat from plasma, it's boiling. Kind of think of it like a double boiler on the stove when you want to melt chocolate. You're keeping that boiling water is keeping the pan inside from getting too hot. Very similar when you hit these engineered solutions boiling temperature, which is usually between 49 and 56 degrees Celsius, depending on the fluid, it means it very rapidly ejects the heat by boiling. So as a result, you can get things much, much denser, even then in a single phase environment where we can have very, very hot components as close as 4 millimeters apart from each other. As long as we can get enough fluid in there, it just boils away the heat and actually requires even fewer pumps and is even more energy efficient because most of the action, that heat rejection, is simple boiling, evaporation, hits a condensing coil, most of it drips back down. So very few pumps are required to circulate the fluid.
Interesting. So you mentioned sustainability a little bit earlier and just talking about having a more sustainable mindset and outlook on things. How does this, what we're talking about here, when it comes to liquid cooling, how does that play into a sustainability conversation?
The first and foremost is energy efficiency. Oftentimes in data centers, you'll hear referred to as PUE, or power usage efficiency or effectiveness. And what that essentially is a ratio of how much energy is going in compared to how much of it is doing useful work. Right now, most of the world has an average, PUE of around 1.5 to 1.6. Essentially, it means you take 1,500, watts in, about 1,000 of that's doing useful work, and 500 of it's doing other stuff like cooling, usually with fans and air conditioners and things like that. With immersion, it is extremely possible and has been demonstrated multiple times. You can get a PUE down below 1.1. So significantly more efficient, using less than 10% of your energy to do things like cooling. So obviously, the more energy efficient we can make things, the more sustainable it is. Along with that, all these engineered fluids, they're designed to last for decades. So you're not constantly replacing that fluid. You might replace the equipment that goes into the fluid, but it can be utilized for a very long period of time. Through multiple generations of server products, which means you're not constantly replacing heat sinks, you're not redoing racks, you're not redoing different cabling and everything else.
That makes sense. That's a really good point, and I think very well explained. So tell us a little bit about what UNICOM Engineering provides in this particular world of liquid cooling.
Yeah, so at UNICOM Engineering, we've been doing liquid cooling for a number of years now. We have multiple partners, including folks like Dell's OEM Group, Intel's Data Center Solutions Group, and HPE that we work with, not just on their direct-to-chip liquid cooling, which is fairly easy to do now. You're just replacing heat sinks, but also taking their products and working hand in hand with their engineers to transform them to immersion-ready products. There are multiple things you want to do to a standard air-cooled server to get it ready to go into a tank. And then beyond that, we work with them to do supplementary support around them. Your regular field technician for any even tier 1 OEM isn't ready for immersion yet. They're not expecting to go on site when a power supply needs to be changed and have something pulled out of a tank of oil, clean it off, replace the power supply, and then because of the modifications made, they might not even have the right part. So we work directly with our partners to make sure that those systems, regardless of their type of liquid cooling, are supported the same way they would expect to buy any server off the shelf today.
Fantastic stuff. So, Austin, as we start to wrap up this episode here today, what do you hope people walk away with? What do you want some of the key takeaways to be from this particular episode?
A big thing is liquid cooling is here now, and if you're not beginning to work with it and understand it, you should quickly, because in these next few years, like I said, in order to keep that density and that performance, especially in a given space, liquid cooling is going to be not just the future, but it's the present.
Very, very well put. Austin Hypes, Chief Technologist and VP of Engineering at UNICOM Engineering. Austin, thanks so much for joining us today.
Great. Thank you.
Absolutely. Thank you so much, Austin. And everyone out there, thank you for joining us for this episode of the show. We appreciate it very much. Of course, for more, you can always visit the UNICOM Engineering website to stay up to date with the latest news and information from UNICOM. And of course, you can find more episodes of the show there as well. But for this episode, for Austin Hypes, I'm Tyler Kern. We'll talk to you next time.